We saw previously that compression can be used to reorganize data so that it takes up fewer bits. In this class, we'll begin looking at ways to compress images. A color image coded using the RGB system would use 8 bits for red, 8 bits for green, and 8 bits for blue. That's 3 bytes in total for each pixel. If an image was 800 by 600 pixels in size, it would have 480,000 pixels in total. At 3 bytes each, that's about 1.2 megabytes. So in digitizing images, 2 factors contribute to the size. The resolution, or the number of pixels, and the pixel depth, or number of bits per pixel. The 2 compression strategies we're going to look at in this class each try to tackle one of these factors. The first strategy is subsampling. Suppose we discarded every second row of pixels and every second column. The 800 by 600 pixel image would be reduced to 400 by 300 pixels. This would give a total of about 0.3 megabytes, or 1/4 of the original size. This is one strategy that can be used for reducing the amount of data in an image. It might seem a bit simplistic to reduce the amount of data you have by throwing some of it away, but if intelligent choices are made about which data is discarded, this can actually be successful. Intelligently discarding information in this way is known as subsampling. Subsampling effectively reduces the sampling rate of the data. In images, this reduces the total number of pixels. But how can a small image be used in place of a large one? Suppose the 800 by 600 pixel image was intended to fill an entire screen. What happens now that it's only half the size? Well, as we've seen before, pixels don't actually have any inherent size. They will shrink or expand in order to fill the space they need to display. So if this subsampled image, with only half the dimensions of the original, was displayed at the original size, then we would see some pixel doubling. This means that the size of each pixel would be twice that of normal. Here's an example of an image displayed at original resolution and with pixel doubling. Now, the compression algorithm used to generate this video might distort the effect somewhat, so you should also download the image separately to look at it. You can see that sometimes the larger pixels are quite noticeable. This, incidentally, is the same problem that you encounter if you take a low-resolution image, say one taken from a web page, and print it at A4 size. The large pixels will be very noticeable. One way to avoid unsightly large pixels is interpolation. Interpolation compensates for the lack of pixels by mathematically hazarding a guess as to what the missing pixels should look like. Consider this missing pixel here. If the pixel to the left of it is red 220, green 0 and blue 0, and the pixel to the right of it is red 180, green 0, blue 0, then it might be reasonable to conclude that the missing pixel between them would have a value of red 200, green 0, blue 0. That value is halfway between them. Interpolation is never as good as having the actual pixel values, but it can make an image look better by making the pixels less noticeable. Interpolated images tend to appear slightly blurry. The subsampling example we considered removed every second row and every second column from the image. In general, however, any image can be displayed at any size. When this happens, sophisticated algorithms determine what the new pixel values should be. So subsampling reduces the number of pixels in an image in order to reduce the file size. The other factor that contributes to the size of an image is the pixel depth, or the number of bits per pixel. If that can be reduced, then so can the file size. Most full-color images use the RGB system and typically use 8 bits per channel. That's 8 bits for the red, 8 bits for the green, and 8 bits for the blue. That gives a total of 24 bits per pixel, so each pixel can be one of 16 million different colors. But suppose 16 million colors weren't needed. Very often images restrict themselves to a few ranges of colors. A photograph of a tropical island might be limited to ranges of blues and greens, and not have need for any reds or yellows. A night shot might be limited to a subset of the 16 million colors possible with 24 bits. If a limited number of colors was used in an image, then it would be possible to use fewer than 24 bits for each pixel. If fewer than 256 colors were used, then only 8 bits would be required to give each pixel color its own unique bit sequence. Suppose an image used only 16 different colors. Those pixels would need only 4 bits each. One color might be 1000 and another 1001. Now that's all very well, but when presented with a sequence of 4 bits in a row, how is a computer going to know what color it represents? A 24-bit sequence represents the RGB values of the color, but 4 bits by itself means nothing. If you think back to the ASCII system for text, you'll recall that the bit sequences by themselves meant nothing unless you had a table in which to look them up. Well, an image can have a color lookup table. A lookup table holds a list of bit sequences and the RGB values of the colors that they represent. In this lookup table, the bit sequence 0000 is used for pixels with the color red 255, green 0, blue 0. And the sequence 1001 is used for 255, 128, 128. Each image coded this way would need its own lookup table to be stored with it. The lookup table is sometimes called a palette or color index. Image editing applications like Photoshop can easily calculate an appropriate palette for an image. The palette used would depend on the colors that appear in the original image. This image of an old £1 note has a palette with mostly greens. There is a little bit of pink and red there to account for the red text. This colourful shopfront, on the other hand, has several strong colours, and that's reflected in its palette. When circumstances force one image to use another image's palette, we have what's known as a palette clash. This is what an attempt to display the pound note using the shop palette would look like. And here is the shop with the pound note palette. Now, so far we've just considered situations where there are few colours in the RGB image, and so we can recode them using a lookup table. More often than not, we can force an image to have fewer colours. It's very common to take a 24-bit RGB image and to code it using a 256 colour lookup table. That uses 8 bits instead of 24. It's easy to imagine how that would work if the original image has fewer than 256 colours to start with. But if the original image has more than 256 colours, how can they fit into such a small palette? Well, they can't. Some colours will be left out. So there will be pixels in the original image for which there is no corresponding colour in the lookup table. A pixel in this situation will be assigned the closest colour that is available in the lookup table. Depending on the image, this compromise can work quite well. Very often a 24-bit image can be reduced to 8 bits without any noticeable differences. Here you can see the effects of reducing the number of colours in an image from 16 million colours to 256 colours, 128 colours, and 64 colours. If the number of colors gets very small, however, the quality is eventually compromised. When selecting a subset of colors for the color palette, the computer must choose carefully based on the colors in the image and adapt the palette to those colors. However, a number of predefined off-the-shelf palettes are available for use too. There may be an occasion when it's desirable to have several different images all use the same palette, so standard palettes can be useful. For many years, web designers have been very concerned that an image should use the web-safe palette. This was a palette of 216 colors that was guaranteed to be available to all browsers on all platforms. This was way back when many people had monitors that could only display 256 different colors at a time. There are very few of those monitors left now. Mind you though, lots of portable devices like phones and PDAs have limited displays. So you might need to know about palettes if you're working with those devices. So we've seen that there are two things that contribute to the file size of an image. There's the number of pixels and the number of bits used for each pixel. If we can reduce the number of pixels, we can reduce the file size. But if the new image is displayed at the original size, we might find that the interpolation causes some blurring. We can also reduce the number of bits used for each pixel. This involves using fewer colors than in the original image. But if we choose our subset of colors carefully, we can be quite successful.